Hey, Dr. Clark, coming back at you with one more example video on section 7.5, impulse forcing in the Dirac delta function. Let's jump in. So example 3 here, we're coming back to a underdamped harmonic oscillator by the look of it. And but this time we've got a couple interesting things happening on right-hand side. First, we've got a Dirac delta coming in at time t equals 3. So the solution is going to happen, and then at t equal to 3, we're going to change the velocity instantaneously. The other thing we're going to have is just a constant force turning on. So remember that unit step function, it's going to be 0 up until time equals 1, and then it'll start being equal to 1 at t equals 1. So if you kind of think about what the solution to that might be, let's just think about it a second. You've got some, what's this? Underdamped. So starting at 0, initial position 0, initial velocity of 2. So the initial solution should come off at a slope of 2 from the initial position of 0. And then because it's underdamped, it should kind of, that maybe wasn't quite great, but, it should kind of do something like that, right? Oscillate close down to 0. That's not what it's going to do, though, because starting at t equals 1, you're going to start pushing it. And so it's going to try to kind of level off at some constant value in response to that forcing term, depending on how strong that force is. And then at 3 seconds, right, when you're thinking you're going to level off, you're going to change its velocity, and then it's going to probably kind of oscillate back down, settling in at wherever that, response to the forcing term is. So, right, because you've got a constant external force happening. So what this solution is going to look like is going to be some combination of a bunch of different functions, accounting for the initial conditions, that force that turned on at t equals 1, and then that change in velocity, but that's going to eventually sort of die away. That'll be a transient term. And so in the end, we should just sort of asymptotically come close to the just the solution, the particular solution, essentially, in response to the forcing term. And if I was going to look at it again myself, I would say that if this is basically a force of 1, and then you have 10y here, then that's probably going to be 1/10, right? Because the spring is a force of, the spring constant is 10. So if you're forcing it with 1 Newton, it's going to settle at 1/10. So after the dust settles, I would think that this function is going to settle down at 1/10, something like that. Okay, but let's jump in and actually tackle it here. If you don't mind, let's just do left-hand side first, and then we'll do right-hand side. So we're going to have, on the left-hand side, we'll have S L of y prime minus y prime of 0 plus 2 times S L of y minus y of 0 plus 10 L of y. That's just Laplacing the left-hand side. Y prime of 0 is 2, so this is going to be 2, and y of 0 is 0, so that's going to go away. And then we still have L of y prime, so we're going to need to run that through the derivative formula for Laplace transform. So then we get SL of y minus y of 0. Of course, y of 0, that's 0, so that will just cancel out. We'll have 2s. Well, I forgot this. What was that? Minus 2 from y prime of 0, and then plus 2s L of y plus 10 L of y. And so when you collect together the Laplace transform of y, you're going to get s squared plus 2s plus 10. That's the characteristic equation. And the only thing that's left, I believe, is just minus 2. Because y prime was equal to 2, so that came out, but then the y terms, y at 0 ended up just going away, essentially. Okay. So with that in play, let us take a look at the right-hand side. Yeah, so right-hand side is going to be what? U t minus 1 plus delta t minus 3. So what is L of u t minus 1 plus delta t minus 3? Well, the unit step function, that's just going to be e to the, what is that, minus as, so e minus 1s over s. That's how the unit step function works. And then delta t minus 3, that's just going to be e to the minus 3s, basically, right? Because t is at t equals 3. And then for the unit step function, it's happening at 1. So you get e to the minus 1s divided by s from just the Laplace transform of that. So if we put these two bits together, we're going to have s squared plus 2s plus 10 times L of y. There was a minus 2, so that's going to add to 2 on the other side, e to the minus s over s plus e to the minus 3s. And so after the dust all settles, you get L of y equals 2 over s squared plus 2s plus 10. Then we're going to have e to the minus s over s times s squared plus 2s plus 10 plus e to the minus 3s 1 over s squared plus 2s plus 10. Okay, and I suppose we're going to need to copy this over to the next page here and get started with it. So a couple things to notice. First, we're going to have to do partial fractions on that term right there. Right. These other terms, these are going to be fine because those are just going to be, well, that's going to factor into that s plus 1 squared plus 9. I think we've seen one kind of like this in a previous example. But that doesn't work here because we've got the s term there. So let's see if we can handle 1 over s parentheses s squared plus 2s plus 10 written as a over s plus bs plus c over s squared plus 2s plus 10. Of course, that's sort of that irreducible quadratic, so that's why we've got the linear term in the numerator. Clear out the denominators. You're going to get a times s squared plus 2s plus 10, and then you'll have bs plus c times s. And I think we can figure out a if we just set s equal to 0, you'll get 1 is equal to 10 times a because this s will make that all 0. And then, of course, these two s's here, they're going to be 0 as well. So you just get 10a. So a is equal to 1/10. All right. And if I think about just multiplying this out, then we're going to have 1/10 of s squared, 2/10 of an s, and then 1 plus bs squared plus cs. And the way I see it, we've got a couple things that are nice. 1 equals 1, so that's good. There's a 1/10 of an s squared, and there's bs squareds. You don't have any s squareds on left-hand side, so that means you're going to need b to equal negative 1/10, so the s squareds cancel. So b is going to be negative 1/10. And then c, well, there's, what else do you have here? You've got 2/10 of an s, and then you have cs's. So that c is going to have to cancel out that 2/10 of an s. So c must equal negative 2/10 s, or negative 1/5. Let's see if I can write that 5 a little more clearly for you. Okay, so that means that if we, let's see if we can't clear out some of this stuff here. A is 1/10, so let's just write that there. There's 1/10. B is negative 1/10, so let's write that there. And then c, that was 1/5, negative 1/5. So let's write that there. Okay. And then, of course, that was 1 over s times s squared plus 2s plus 10. It had an e to the minus s, so that would have to be multiplied onto both of those terms. Okay. So let's rewrite on the next page what we've got here. So we've got L of y equals, we had 2, and that is s plus 1 squared plus 9. That's what s squared plus 2s plus 10. 10 is equal to 1 plus 9, and s plus s squared plus 2s plus 1 is equal to s plus 1 squared. So that factors into those sort of two parts like so. And then I'm going to have plus e to the minus s times, well, there should be something over s, so 1/10 over s, so 1/10 times 1 over s. And then e to the minus s times this second term, which will be negative 1/10 s plus negative 1/5. So negative 1/10 s minus 1/5 all over s plus 1 squared plus 9, right? That's what this term is here, okay, right here. And then we've got the last term, which has an e to the minus 3s on it. So plus e to the minus 3s times, was it just 1? Yeah, just 1 over s plus 1 squared plus 9. Again, that's just the characteristic equation right here, factored into that s plus 1 squared plus 9. Okay, and so we can find a y by just inverse Laplacing each one of these terms here. Okay, and I think that's going to be not too tough for some of these, but this one in particular looks to be maybe a little bit messy. So let's handle them one at a time here. Let's call this, we'll do this one first, we'll do this one second, we'll do this one third, and we'll do that one fourth. So number 1, what is y of t going to equal? We'll call that y1 of t, and then we'll add the 4 y's together to get the final answer for y. Okay, so that looks to me like it's of the type, well, we've got 2. I think I'm going to write that as 2/3 and then 3 over s plus 1 squared plus 9. So that's looking like sine to me. But it would be sine if it was s squared plus 9. But we've got that s plus 1. And that's what happens when s is replaced with s plus 1. That means that you've multiplied by e to the minus 1t in the time domain. Remember, multiplication by e to the t becomes a shift in the frequency domain. And that makes sense because this is underdamped. We should have e to the minus t sine of 3t. That's exactly the kind of solution we should be looking for. So y1 of t is going to be 2/3 e to the minus 1t sine of 3t, right? This is causing the e to the minus 1t, and the fact that that's 3 squared is causing us sine of 3t. Okay, so there's number 1. And I think we can maybe fit number 2 on this same page. So let's see if we can handle that. Okay, so we've got 1/10. That's probably just going to come along for the ride. We've got 1 over s. Well, that's just the Laplace of a constant. So L of 1/10 would just be 1/10 1 over s, right? So if we didn't have e to the minus s, we would be done with 1/10. But e to the minus s, that comes back, right, as essentially treating it as a shift, right? So we've got to shift the 1 over 10 function, but of course 1 over 10 is a constant, so when you shift it, nothing happens. But then also turn it on at t equals 1. So we need times u t minus 1. So remember, how does this work? When you have an e to the minus s times something, you just write down the something, and then you shift it, and then turn it on at that time, in this case, 1. Okay, so that's y2. The third one here, let me just copy this and paste it onto the next page. so we can get a look at it here. So this is going to be number 3. So we're going to have y3 of t once we inverse this. I think there's going to be some work to do here because what we need is this has to look like s plus 1 squared plus 9. This really has to look like s plus 1. So I think what I'm going to do is factor out. Is there a minus on there? No, there's no minus. I'm not sure where that minus came from. I think what I'm going to do is factor out negative 1/10 and the e to the minus s. That leaves you with an s, but I think we're going to have to write plus 2 because 2 times negative 1/10 would give you negative 1/5. Okay? And so that helps a little bit, but s plus 2 isn't quite right. What we really need is s plus 1, right, over s plus 1 squared plus 9. But then I can just write that as 1 over s plus 1 squared plus 9 because 1 plus 1 is 2, right? So I can separate it out, but then both of these are going to be multiplied by negative 1/10 e to the minus s, okay? All right, so this one looks like cosine, and this one looks like sine, right? So the generic form is s over s squared plus 9. That's cosine. It's like cosine of 3t, right? This will be sine of 3t. Although technically we should really have a 3 there, so we're going to need a 1/3. So that's going to be 1/3 sine of 3t, okay? And then what else do we need? Oh, okay, we got a negative 1/10, so that's fine. We'll just multiply by negative 1/10. So that becomes negative 1 over 30, I guess. And then e to the minus s. So when you have an e to the minus s, you're going to have to shift it over, in this case, 1 second, and then turn it on at t equals 1. So the final answer for y3 is, if I can slide this sort of out of the way here, we should have negative 1/10 cosine of 3 shifted by 1, so t minus 1, and then turned on at t equals 1. And then we'll have minus 1 over 30 sine 3 shifted by 1 and turned on at t equals 1. So that is a challenging one to handle right there, but you got to do it kind of step by step, thinking through what's the basic shape and then where are the shifts happening and that kind of thing. All right. And then we've got number 4. Let me just copy number 4 here onto a new page, and let's tackle that one. So this will be y4. This looks like, well, I'm going to need a 3, and then I guess I'll have a 1/3. So this is looking like sine of 3t times e to the minus t. Oh, did I forget the e to the minus t? I might have forgotten that on the last page here. Yes. Oh, I forgot. So when you have s plus 1, that's telling you it's e to the minus t. So all of this needs, caret here, e to the minus t, but t is going to be replaced with t minus 1 there. And we're going to need an e to the minus t minus 1 there as well. Ooh, okay, almost missed that one on there. So this one should be a little more easier. So this really should just be e to the minus t times sine of 3t with a 1/3. That's what this would give you, right? 1/3 e to the minus t sine of 3t. But because we have the e to the minus 3s, that's not going to be right. We're going to have to shift it by 3 minutes, or t equals 3, and then turn it on at t equals 3. So that's not quite right. We're going to need 1/3 e to the minus t minus 3 sine of 3 t minus 3 times u t minus 3. Turn it on at t equals 3. All right. And I don't want to recopy all of them, but the final answer would be essentially y1 plus y2 plus y3 plus y4. So a lot of pieces here. So we have this. Now, remember, this all does look like the kind of thing we should see, right? This is an underdamped solution, right? So the underdamped is at e to the minus t sine of 3t, right? That's underdamped. This one's turning on at t equals 3. These are turning on at t equals 1. And then these ones here are, well, this one turns on at t equals 1 as well. And then that one is just the original homogeneous solution. So if we go back to the very beginning, why are there sort of 4 pieces to this answer? Well, the initial conditions give you that first solution. And then ut minus 1, well, that turned on that constant function, right? So that gave us that 1/10 ut minus 1. But then the differential equation has to equalize the continuity of position and velocity. So you get another term that pops up at that point, right? You get this, this solution, well, here, but then also here, this y3 is really turning on at t equals 1 to balance the, so that you don't have a discontinuity essentially. And then this fourth solution here, that one is coming from the Dirac forcing, which happens at t equals 3. So then that Dirac turns on a sine function essentially to give you that initial, that change in velocity. So this is certainly a more challenging problem in that the solution is, I kind of add up all these little pieces together to get the answer. But if you kind of do it step by step, each piece is its own thing. You just have to inverse each piece separately and think through, use your formulas for the basic functions, and then your translation formulas, and then your e to the minus s when you got those Diracs, that shifting formula. Okay, so it's a more challenging problem, but hopefully you were able to follow it. And if you were, good job, and we'll see you in the next video.